In this video, we're going to look at partial pressures. We're going to use Dalton's law to calculate partial pressures and total pressures. We're also going to look at mole fractions. Dalton's law of partial pressures, the total pressure exerted by a mixture of gases is the sum of the partial pressures of the component gases. So if we have a container with several different gases in it, the total pressure exerted by the mixture will be the sum of the partial pressures of each of those gases. If we had two ideal gases, A and B, Dalton's law could be expressed as P total equals partial pressure of A plus partial pressure of B. You'll often see Dalton's law expressed in this way. But if we think about the ideal gas law, we can also express it as the number of moles. So therefore we can express it as pressure total equals number of moles of A times RT over V plus number of moles of gas B RT over V. Or we can convert that into pressure total equals the number of moles of gas A plus the number of moles of gas B times RT over V. As you can see here, we're expressing the pressure total by the sum of the number of moles of the gases. This means that we can now express it in terms of mole fraction. If we look at the mole fraction of A, given by X subscript A, is the number of moles of A over the total moles, or NA over NT. If we relate this to partial pressures and total pressure, we can see that PA PT over NA times RT over V over NT times RT over V. We can show, as you can see here, RT then cancels, giving us NA over NT, and we know that A over NT is the mole fraction for A, so therefore PA over PT is related to XA. We can then convert that into the formula PA equals mole fraction A times the pressure for the total. Okay, let's use these two expressions and work two different problems. First problem, what is the partial pressure of each gas if 1.65 moles of propane, C3H8, and 0.920 moles of carbon dioxide are placed in a 30-liter container at 25 degrees Celsius? What is the total pressure? So if we analyze the question here, it's giving us some information, but it's actually asking us two things. One, we're going to need the partial pressures for each, the propane and the CO2. And it has a second question. What is the total pressure? So we're also going to have to calculate the total pressure. We know that it gives us a number of moles of propane and CO2, and it gives us the volume and the temperature. We can calculate the pressure by using PV equals nRT. If we convert PV equals nRT to get pressure by itself, we'll see that we get nRT over V. For partial pressure for propane, we just need to plug in our values. So 1.650 moles times the constant R times 293.15 Kelvin, which is the conversion of 25 degrees Celsius to Kelvin, divided by 30.0 liters. We do that calculation, we look at our significant figures, and we see that our answer here is going to be the partial pressure of propane is equal to 1.32 atmospheres. We can do the same calculation using P equals nRT over V for the partial pressure of CO2. Here we have partial pressure of CO2, plug in our values, 0.920 moles times the constant R times 293.15 Kelvin, which is the conversion of 25 degrees Celsius, divided by 30 liters. That gives us a partial pressure of CO2 of 0.738 atmospheres. So we've answered the first question, the partial pressures. Now we have to do total pressures. Remember, there's two ways to do this. One way, we can look at partial total is equal to the partial pressures of propane plus the partial pressure of CO2. We already calculated these, so we just have to plug them in. So the total pressure is going to be 1.32 atmospheres plus 0.738 atmospheres. Add those together, remember our significant figures, and we come out with the total pressure equals 2.06 atmospheres. At this point, we've answered our problem, but we can check it by using the other expression for pressure total where we relate it to the number of moles. So we can take the values directly out of the question, 1.650 moles plus the number of moles for CO2, 0.92 moles, and we can put that in the formula number of moles of propane plus number of moles of CO2 times RT over V. We plug all those values in, we do our calculation, again following significant figures, and we come up with the pressure total of 2.06 atmospheres. Now let's look at calculating the ratio of moles of a gas from the partial pressures and total pressure. For that value, we're going to look at this problem. What is the mole fraction of CO2 in a mixture of gases with a partial pressure of CO2 of 1.75 atmospheres and of nitrogen of 0.425 atmospheres? So in this case, we're given the partial pressures. So we can remember that the mole fraction of CO2, which is what the question is asking for, is going to be the partial pressure of CO2 over the total pressure. We have the partial pressures of both CO2 and nitrogen, but not the total pressure. We can calculate the total pressure by adding the two partial pressures. So P total equals partial pressure of CO2 plus the partial pressure of nitrogen. We can look those values up. Partial pressure of CO2 is 1.75 atmospheres from the question. Partial pressures of nitrogen is 0.425 atmospheres from the question. We put those into the formula, add those together, and we get a total pressure of 2.18 atmospheres. Now we have both the values we need to calculate the mole fraction. So we take the mole fraction as the partial pressure of CO2 over the total pressure. So 1.75 atmospheres over 2.18 atmospheres. Do our calculation, and we come up with the mole fraction of CO2 of 0.80. Notice in this case that we do not have any units because partial pressure of CO2 is in atmospheres and the total pressure in atmospheres, so those cancel, leaving us a unitless quantity. Practice partial pressures, calculating total pressure, and mole fractions. Practice and become confident.